everyone, welcome back to Binary Builders, where we break down data structures and algorithms into simple and powerful concepts. In today's video, we are diving deep into the AVL trees, specifically node deletion, and how to rebalance the trees when things go wrong. If you're learning advanced trees for exams, interviews, or projects, this video is going to help you a lot. So, let's get started. First, what exactly is an AVL tree? An AVL tree is a self-balanced binary search tree. It was invented by Adelson Wilsky and Landis, and that's where the names AVL comes from. The key idea is after every insertion or deletion, the tree automatically balances itself. How does it do that? By using something called the balance factor. Balance factor equals to height of left subtree minus height of right subtree. For a valid AVL tree, balance factor must be -1, 0 or +1 for every node. If it becomes less than -1 or greater than +1, the tree becomes unbalanced. The rotationals are needed. So AVL trees are just BSTs that never allows themselves to get too tall or skewed. Insertion usually makes tree heavy, but deletion is trickier. Why? Because removing a node can suddenly reduce the height of the subtree. Imagine deleting a node from the left subtree. The left height decrease, balance factor might shift to the right. If the balance factor goes outside the allowed range, that -1 to +1, we identify the imbalance and fixed it. Key things to remember during deletion. First one is perform normal BST deletion first. If it is a leaf, remove directly. If it is one child, replace with child. If it is two children, replace with the in-order successor. The second thing is update heights of all ancestor nodes. Then check balance factors from the deletion nodes ancestor upwards. Perform appropriate rotations if any nodes becomes unbalanced. Once we detect a node that become unbalanced, we classify the imbalance into 4 types, just like insertion. First one is left-left case. This occurs when balance factor is greater than 1 and deletion happens in the left subtree of the left child. The solution is right rotation. The second one is left-right case. This occurs when balance factor is greater than 1 and deletion happen in the right subtree of the left child. The solution for this is left rotation on the left child, then right rotation on the unbalanced node. The third one is right case. This occurs when balance factor is lower than -1 and deletion happens in the right subtree of the right child. Solution is left rotation. The fourth one is right-left case. This occurs when balance factor is lower than -1 and deletion happens in the left subset in the right child. The solution is right rotation on the right child, then left rotation on the unbalanced node. During deletions, RR and RL rotations are more common because deletion from the one side often reduce height and shift balance toward the opposite side. But the trick is simple. Find where the imbalance originates and rotate accordingly. Now, let's walk through a simple example. Consider this AVL tree. 30 is the root node of the tree. It has two children. Left child is 20, right child is 40. Node 20 has left child is 10. Now, suppose we delete 40. After deletion, the tree become like this. The right subtree of 30 has height 0. The left subtree has height 2. when we got balance factor of 30 is equal to 2 minus 0 is plus 2. This means the tree is unbalanced with LLKs. So we performed right rotation on the 30. After rotation, the tree becomes like this. Now the tree is perfectly balanced again. And that's the magic of the AVL trees. They fix themselves automatically after operations. Next, we delete a node with a one child. Consider this tree. Node 88 has a child 99. In this case, we replace the node 88 with its child 99. 99 move up to take 88's position. Now, we update heights and balance factor. The AVL property is still satisfied. Next, we delete a node with two children. Now, the interesting case, deleting node 55, which has two children, 35 and 68. For two children node, we replace it with the in order successor with which is 68. Uh, First, copy 68 node to the 55, delete the original 68, update height and balance factor. After deletion, the subtree height changes, but the AVL tree automatically rebalance it if needed. And that's it for today's tutorial on AVL trees deletion and rebalancing. If you found the explanation helpful, don't forget to like, subscribe, and comment your next topic below. This is Binary Builders breaking down complex algorithms into simple logic. See you in the next video.